In this section, we will discuss an introduction to the normal probability distribution. The normal probability distribution is the most popular and important distribution for describing a continuous random variable. This distribution has been used to define the heights and weights of people, test scores, and IQ scores. The normal distribution is widely used in a variety of statistical inference techniques. Recall our steps for computing probabilities for the continuous random variable. In step 1, we graph the probability density function for the variable. Therefore, in order for us to compute probabilities for a normal random variable, we must learn about the probability density function for this variable. On this slide, we have the density function for a normal random variable. Luckily, this density function has some very basic properties which will allow us to easily draw this density function. This distribution is symmetric and illustrated as a bell-shaped curve. There are two main parameters that define this distribution: the population mean and the population standard deviation. These measures determine the location and shape of the distribution. Here we see that the normal curve is drawn as a bell-shaped curve. The highest point on the normal curve is at the mean, which is also the median and the mode. In order to illustrate how the normal curve gets its shape, let's think about drawing a histogram for a normally distributed population, and then drawing a line over the top of all of the bars of our histogram. If we did this, we would obtain a normal curve as shown on this slide. The highest bar in the histogram would occur at the mean. This indicates that the mean is the value that occurs the most frequently in the population. For this reason, we say that the mean is also the mode. Also, for a continuous random variable, we know that the total area under the density function equals 1. Since the normal curve is symmetric about the mean, half of the area under the curve is to the left of the mean, which indicates that half of the values in the population are less than or equal to the mean, and half of the area underneath the curve is to the right of the mean. This indicates that half of the values in the population are the mean value or greater. For this reason, we say that the mean is also the median for this distribution. The mean value can be negative, 0, or positive. Recall the empirical rule. The empirical rule states that for normally distributed data, 68.26% of the values will fall within one standard deviation of the mean. 95.44% of the values will fall within 2 standard deviations of the mean. And almost all values, or 99.73% of values, will fall within 3 standard deviations of the mean. In the Computing Normal Probability section, we will learn how all of these percentages are computed. When drawing our normal curve, we should start by drawing a bell-shaped curve that is symmetric about the mean. According to the empirical rule, this curve should be drawn on the x-axis between the values, the mean minus 3 standard deviations and the mean plus 3 standard deviations. Let's practice drawing a few density functions for normally distributed data. First, we have normally distributed data with a mean of 40 and a standard deviation of 2. We draw our normal curve with the highest point occurring at the value 40, and our lower endpoint for this curve should occur at 34. We obtain the value 34 as the mean, which is 40, minus 3 times our standard deviation of 2. 3 times 2 is 6. So 6 below the mean gives us the endpoint 34, and the mean plus 3 standard deviations, or 6 above our mean, gives us the higher endpoint value of 46. Let's draw the density function for normally distributed data with a mean of 100 and a standard deviation of 15. You should pause the video at this time and draw this curve. You should have drawn a curve with the highest point occurring at 100, and your lower endpoint value should be 55, that's 3 standard deviations below the mean, and your higher endpoint value should be 145, which is 3 standard deviations above the mean. Now suppose we have normally distributed data with a mean of 100 and standard deviation of 15, and we want to compute the probability that x falls between 80 and 135. According to our steps for computing probabilities for continuous random variables, we begin by drawing the density curve for this example. Here we draw our normal curve with a high point at the mean 100 and our endpoints at 55 and 145. We then shade in our interval of interest. Here, since we want the probability that x falls between 80 and 135, we shade in the interval on the x-axis between the number 80 and the number 135. We then shade in the area underneath our curve in this interval of interest. Now, we must determine this area in order to know the probability that x falls between 80 and 135. We could compute this measure directly using calculus and setting our integrands between 80 and 135 and just performing integration on this density function for our mean and our standard deviation. Or we can use an alternate approach. For most of us, since calculus and integration probably wasn't one of our favorite topics, we can discuss some common characteristics and patterns that exist within normal distributions in order to come up with an alternate approach for computing probabilities for normal random variables. In order to discuss or even explore the common thread between all normal distributions, let's review these two examples. For our first example, we have normal data with a mean of 100 and a standard deviation of 15. For this example, we want to compute the probabilities that x falls between 55 and 80, that x falls between 130 and 145, and that x falls between 80 and 130. For our second example, we have normal data with a mean of 70 and a standard deviation of 6. For this example, we want to compute the probabilities that x falls between 52 and 62, the probability that x falls between 82 and 88, and the probability that x falls between 62 and 82. For now, in order to explore the common thread between probabilities, we are going to use the Seeing Statistics website. Go to the website listed on this link. Now let's go to the Seeing Statistics website. Now on this website, let's enter our mean and our standard deviation. We should also enter the starting value and the ending value for the interval we are interested in. Now if we press enter, this website provides for a normal distribution with a mean of 100 and a standard deviation of 15, the probability that x will fall between 55 and 80. Here, the site tells us that this probability is 0.0899. We will use this website in order to compute all of the probabilities for our examples. For example 2, we'll simply change the mean and the standard deviations, and then change the start and end values for each of our example problems. We used this website in order to compute all of the probabilities listed on the slide. If we look, several similarities exist between both of these examples. For part A, in example 1, we asked for the probability that x falls between 55 and 80, and we obtained a probability of 0.0899. In example 2, even though we had a different mean and a different standard deviation, and we asked for the probability of x falling in a different interval, we still obtained a probability value of 0.0899. If we look in part B of example 1, we asked for the probability that x falls between 130 and 145. We obtained a probability of 0.0214. In example 2, part B, even though this example had a different mean and different standard deviation and asked for x falling in a different interval, we still obtained a probability value of 0.0214. The similarity between these two examples lie with the term that we learned in a previous section called the z-score. If we examine part A for both of these examples, In example 1, we had a mean of 100 and a standard deviation of 15, and we asked for the probability that x falls between 55 and 80. In example 2, we had a mean of 70 and a standard deviation of 6, and we asked for the probability that x falls between 52 and 62. If we convert both of these x intervals into their z-score intervals, then we will begin to see the similarities emerge. In example 1, we use our z-score formula z equals x minus the mean for this data set divided by the standard deviation. Below, we compute the z-score for 55 as 55 minus the mean for this data, which is 100, divided by the standard deviation for this data, which is 15. We obtain a z-score of -3. We then compute the z-score for 80 as 80 minus the mean for this data divided by the standard deviation for this data, and we obtain a z-score of -1.33. For example 2, we apply the same z-score formula. However, we use the mean and the standard deviation for this data set. When we computed the z-score for the number 52, we compute that z-score as 52 minus the mean for this data set, which is 70, divided by 6. This gives us a z-score of -3. We compute the z-score for the number 62 as 62 minus the mean for this data set divided by the standard deviation for this data set, and we obtain a z-score value of -1.33. Therefore, if we look at the z-score intervals for example 1 and example 2, the z-score intervals are identical. The moral to the story: if we look at normal probabilities through the eyes of their z-score intervals, then our probability values become identical. In other words, the probability of z falling in any interval will be the same, regardless of the original population that the data came from. Since there is a common thread between all normal distributions with respect to their z-scores, if we had a single source that provided the area under a normal curve for any z-score interval, we could use this source to determine normal probabilities. The standard normal distribution is our source that we will use to accomplish this task.